Let us motivate this last segment with the following example. Consider the case where there is a countably infinite number of user IDs that's possible that people can use to access a certain web service. And as business starts to pick up, there will be a lot of users joining the web service, and this will mean that out of the possible set, a sizable number of user IDs will be taken up. So let us suppose that S is the set of user IDs that are already taken, and we denote them by S1, S2, and so on up to Sm. Now, given some element from the possible set of user IDs, and let's call this set U for the universe of user IDs. Let's say we have some X, and that belongs to the universe of user IDs. The question is, does the user ID X belong to the set of user IDs that are already taken? This is an important question because as new users come into the system, they're going to try out some user IDs, and if the user ID is taken, then they will have to modify it, and we've all done this before several times, I'm sure. The question is, how does the system retrieve user IDs, retrieve the fact that a particular user ID has been used so quickly? I mean, remember these queries have to go into a database which is probably distributed and found in some particular server somewhere in their data center, and the user ID that you are trying to get you might have to be searched against a lot of user IDs, and so you may wonder how this works, and we're going to look at some ways in which this can be implemented. But here's something that I would like you to keep in mind or try to remember. There are times when you might have tried some user IDs, and then you would try some slightly complicated user IDs, add a few numbers, and so on and so forth. And I'm pretty sure you might have been surprised that even these complicated user ID variations were rejected until you found one. And that's potentially because the system they are using behind the scenes is one that has a certain fraction of false positives. Even though some user IDs aren't actually taken, the system may say that that user ID is taken. But one important aspect is that the system will never allow you to use a user ID that has already been used. So in other words, it does not allow a false negative. It only allows a false positive. So that's something to keep in mind, and that might show up as we continue in this discussion. Let us first look at a first cut approach. We're going to look at the fingerprinting approach, wherein we're going to use a hash function. So every time a user ID is included into the set S, the ID is hashed, and a smaller fingerprint, basically the hash value, is going to be stored in a manner that it can be easily searched for each user ID S from the set of user IDs that we have included so far. H of S is the hash value of S, and it's also called a fingerprint. Basically, it's a way to identify the user ID S, and these fingerprints have to be stored in some dictionary. So, for example, let us consider the case where these fingerprints, these hash values, are stored in a balanced binary search tree. So, when we have to check whether a particular user ID is already used, then we have to compute the hash value of the user ID that we need to check. And using the hash value, we search in the balanced binary search tree and check to see if that hash value is present in the balanced binary search tree. Now, if the hash value is not in the balanced binary search tree, then for sure we know that that user ID is not taken so far. So no false negatives are allowed. However, if the hash value is in the balanced binary search tree, that is only evidence that the user ID is possibly taken. It's not guaranteed, because multiple items from the universe could potentially hash into the same fingerprint. So unlike human fingerprints, these are not unique, because typically when we think of these fingerprints, these hash values, they are going to use fewer bits than the number of bits needed to represent each element in the universe. So there is going to be some loss of information, and therefore there is going to be collisions in the hashed values. So there is no guarantee that the user ID is not taken, but nevertheless it's good evidence, and this is why you sometimes encounter false positives where a potentially good user ID is still rejected by the system. This, you may wonder, why not use something like chain hashing? That's a little bit of an overkill, because for chain hashing we actually have to store the items. It's a dictionary. So what we are talking about here is not a dictionary, but really just set membership, which is an easier problem, but a very commonly encountered problem in big data applications. And so we want to solve the set membership problem more efficiently than we solve the dictionary problem. So with that being the case, let's look at a well-known technique to implement the set membership data structure. This data structure is called Bloom filter, named after the person who invented this data structure. To motivate the idea behind Bloom filters, let's start with a preliminary approach. Now let us say that we have a binary array of 2 raised to the b cells, and let's say we have a hash function h that takes elements from the universe and maps them to the indices ranging from 1 to 2 raised to the b. So as each element s, or each user ID s, enters the system, and you can potentially apply this to a streaming setting where each element arrives one by one, and as the element s appears, we hash the element and find the location where it will the index to which it hashes, and set the value in that index position to a 1. I forgot to mention that this binary array is initialized such that all entries are 0 in the beginning. So any time a new item, a new user ID appears, its hash value points to an index location, and that index location, if it's not already set to a 1, will be set to a 1. And so this is one way to implicitly store all the fingerprints. And this certainly is an improvement over using a balanced binary search tree to store all the fingerprints. Because, well, the number, you don't need to store all the bits of the fingerprint. You just have to we are implicitly storing the fingerprints as indices in this binary array, and moreover the query time is just O of 1. When we get a new user ID, all we have to do is compute the hash value and go to the particular index location that it points to see whether that particular index location is set to a 1 or not. The one downside we may need to keep in mind is that we will have to pre-compute the size of the array. While the balanced binary search tree can grow as your business grows and as more user IDs show up, in this technique we have to pre-calculate the number of user IDs that we are potentially going to have in the company, and therefore we need to provision for the appropriate number even before the company takes off, and this could lead to miscalculations, of course. So we need to be careful about that. So this is great, But this is there's something more we can do. Right now we are using a single hash function. Let us now try to understand how the Bloom filter will work when we have access to k different hash functions h1 through hk. So we have 2 raised to the b binary cells, and that's available here. They're all initialized to 0. Now, every time a new item shows up, and here we have item x drawn from the universe, when the new item shows up, here's what we do. We take the item x and hash it using each one of the k hash functions. So let's say h1 of x leads us to this location. So then we will place a 1 in that location. And let's say h2 of x leads us to this location. We would now place a 1 in that location as well. And so, and let's, for example, let's say h3 of x hashes into that location. We would place a 1 there as well. So in those k locations, so we'll continue to do that. And let's say the kth hash leads us here. We will place a 1 there. So as you can see, for each item x that needs to be inserted, we will have to apply the k hash functions, and they all hash into the same table. So in a Bloom filter, we only have one array, one binary array, and each one of the hash functions is used to hash the value x, and this leads each of these hash functions to a particular index, where that index element is then set to a 1. Now, this is how the insertion takes place. Now let's see how we would do a query. So when we want to query an item, we're given an item x, which is drawn from the universe, and we want to find out if that item is actually in the set S that is currently stored in the currently stored in the Bloom filter. And recall, since several items have probably already been inserted into the Bloom filter, several bit locations are already going to be holding ones. But then there's going to be several zeros as well. Hopefully the Bloom filter is not filled with all ones, and you'll see why that would not be a good situation. So let's consider the situation where we have several ones in the Bloom filter array. Now here's what we will do in order to test if x is actually in the set S or not. So we will take each hash functions, the same k hash functions, and we will see, okay, what is h1 of x? Now if h1 of x is leading to an index where we have a 1, we will continue. Let's see where, let's say h2 of x is also leading to a bit position where we have a 1. Let's say h3 of x, however, leads us to a bit position where there is a 0. In this situation, we know that x does not belong to the set S. And why is that? Because had x already been inserted, and remember S is the set of items already inserted into the Bloom filter. So now, when h3 of x leads to a 0 bit, then we know for sure that this particular x value is not in S, because had it been inserted, this location would have been set to a 1. So we know, so then we can immediately say for sure, and we are 100% sure now, that x is not in the Bloom filter. On the other hand, suppose all the hash functions, say h3 of x leads to a 1 and so on, and including, say, hk of x, if all of them lead to indices within the Bloom filter where we see a 1 bit stored, then we will respond saying X is in the set S. And it's easy for you to see that there is still a possibility of having made a mistake. So for example, it could have happened that several different other items, even though let's say X was never inserted, but other items were hashed into the same location, so they all just happen to be ones, and these bit positions which we are querying now were not set by X but were set by other values. So that's very much a possibility. So that is why Bloom filters sometimes have false positives, but they never will have false negatives. Would it help to use more than one hash function? On the one hand, more number of hash functions, we will be able to find a cell that is not set to 1 in case the item we're looking for is not already in the set S. But on the other hand, if we use too many hash functions, for each of the items that we have seen so far, if the number of hash functions we use is too large, then each one of them fills up this binary vector by setting a large number of the cells to ones, and soon all the cells or most of the cells will be set to a 1. So when you encounter a user ID that is not already in the set S, that user ID, when you hash it to the range 1 to 2 raised to the b, since the cells are all already set to a 1, they will all the hash values will fall into cells that are set to a 1, which means that it's going to be which means that we're going to conclude that that particular user ID is already taken, and therefore that's wrong. So that's a problem. So there is a correct balance between too few number of hash functions and too many hash functions. So let's try to understand this balance a little bit carefully now. So let's assume that we have a binary vector of length n, and let's focus on one particular fixed cell. The question is, what is the probability that that particular cell is unset? None of the hash values so far have mapped any of the items to that particular cell so far. What is the probability of that after m items are processed and each item has been processed with k hash function? Well, each of the hash functions will take us to that cell with probability 1 over n. So each time an item is hashed, that particular location will escape being hashed into with probability 1 minus 1 over n. And how will this cell I escape being hashed into when m items have been processed and each one of them with k hash functions? Well, this whole probability raised to the power k times m. And this we all know is approximately equal to e to the minus km over n. Now this value is essentially the probability that a particular cell is going to be unset. So for ease of notation, let's just denote this by lowercase p. So from this we can conclude that the expected number of empty cells after m items have been processed, each with k hash functions, is going to be n times p, or n times e to the minus km over n. Now let us consider the scenario where m items have been processed and each of them has been processed with k hash functions, and now we get a particular item, a user ID from the universe. Let's call that x. The question is, does this item x already belong in the set S? Okay, so what we are going to do now is we're going to take x, we're going to hash it using each of the k hash functions and check to see whether each of the indices pointed to by the hashed values is set to 1. If all of them are set to 1, we're going to say yes, this item x is already in the set S. Of course, this could be wrong with some probability, which we have to analyze a little bit carefully. But on the other hand, with a good probability, we'll have to be able to say find out that this item, if it is not already in S, we should be able to report that it's not already in S. So now, what is the probability of a false positive? Each time we hash x with probability 1 minus p, we're going to have to land in a cell that's already set to 1. And keep in mind that we are, for our current purposes, assuming that x is already in S, but we are using hash functions that obey the simple uniform hashing assumption. And so when x is hashed, given that a fraction n times p fraction, set of items are already filled with ones on expectation, with probability 1 minus p, our hash value is going to fall into a cell that is already set to a 1. Okay, but that's with one hash value. To get a full false positive, all k hashed values should land in cells with cells that are already set to a 1. So that event is going to happen with probability 1 minus p raised to the power k. And let's denote this by f, and let's expand it out to see what it looks like. And so f is going to be 1 minus e raised to the minus km over n, the whole raised to the power k. Now let's make sure our intuition is fitting this this formula that we have. And remember, f is the probability of a false positive. Now you notice that k is appearing in this expression twice. Now let's focus on this appearance. As the value of k increases here, since this quantity is less than 1, the overall value is going to decrease as k increases. So this k must be large. On the other hand, let's focus on this other k. As this k increases, e to the minus k is going to decrease. And if e to the minus k m over n decreases, 1 minus e raised to the minus k m over n will increase. And that's bad because that increases the false positive. So this k is giving us the opposing force, if you will. And to get a good false positive probability, here we want, looking at this k, we want it to be small. So as you can see clearly, there is a tension here. On the one hand, we want a larger value of k, and on the other hand, we want smaller value of k. And this fits neatly with our intuition that we already built, wherein as the number of hash functions increase, on the one hand we see false positives increasing, and on the other hand false positives decreasing. And so we have mathematical evidence that that intuition is in fact correct. So of course the question that remains is, what is the correct k value? And to answer this, let's look at g equals ln of f and see what value of k minimizes g. Because if we can minimize g, then we're also going to be minimizing f. So in order to find the optimal value of k, well, this is classic calculus. We just have to look at dg over dk, and that's going to equal this expression when we differentiate the right hand side here. And as a quick exercise, you can see that this expression gets minimized when we set k to equal n over m ln 2. And substituting this value of k into the expression for f, we get 1 minus half raised to the power k, that's equal to 1 over 2 raised to the k. And substituting the value of k, we're ultimately going to get approximately 0.62 raised to the power n over m. So let's look at the intuition here. N, recall, is the number of bits in the bit vector that we use to store the Bloom filter ADT, and M is the total number of user IDs that are in the set S. So the probability of the false positives drop exponentially as this fraction n over m increases. So that's a very good sign here. From a designer's point of view, this expression is very nice because we can now use this expression to optimize the parameters that we care about. So for example, if let's say f is fixed, the probability of false positives, let's say that gets fixed down to something like 1 or 2%. And let's also say that the number of hash functions that we have at our disposal is some number, say 10. Then we can compute n because, well, we assume we know m. There's an optimal size n for the length of the bit vector. We can so we can use this expression to optimize for n or k or whatever the parameter of interest might be. So the trade-offs are coming out nicely in this expression, and we can just play with these trade-offs until we get the right system for the application at hand. Let's also look at this expression a little bit more carefully and try to get some more insight out of it. Now consider this expression f equal to 1 minus p raised to the power k. What is k in terms of p? Now recall that p equals e to the minus k m over n. And this implies that the value of k equals minus n over m ln p. So let's apply that here. And this is equal to e to the minus ln 1 minus p ln p the whole times n over m. And if you look at this expression, it is clear that this is going to be minimized when p equals a half. And this can be deduced by just looking at the symmetry of the exponent here. This actually has a very nice intuition. What this tells us is that the Bloom filter works best when about half the bits in the Bloom filter are set to a 1 and the remaining half is set to zeros. Such a Bloom filter will not be will essentially look like a random bit string. So when you intuitively think of searching for or asking querying a particular user ID or an item that's not already in the user IDs that are taken, with probability half, each hash function is going to reveal to you that this particular user ID is not yet taken, and you can see the exponential drop in the probability with which we will be able to detect that this particular user ID is not taken as we try out each hash function. So this again gives us some very good intuition. And with that, we have come to the end of our lecture on Bloom filters. And just to recap, we have looked at a classic big data application, the set membership application, which seeks to answer the question: is a particular item in a given in a given set? And in the spirit of big data applications, uh, we are willing to live with some amount of error. In particular, we are willing to live with some small fraction of false positives, and as in return, we would like the Bloom filter to be um, to be uh, compact in size, and it should be capable of handling streaming data, distributed data, so on and so forth. It's basically a sketch of the entire set S, and we saw how we can analyze the Bloom filters, which is the data structure we studied for set membership problem. We saw how the Bloom filters can be analyzed when we make use of the simple uniform hashing assumption. And just to recall what we discussed early on, we looked at the birthday paradox, we looked at how balls and bins can be used to model birthday paradox, and then we looked at chain hashing, which can be used to implement dictionary data ADT, and we used our knowledge of balls and bins, and in particular we analyzed balls and bins for their maximum load, and we applied that intuition into chain hashing to understand how to understand what the query time of chain hashing is, and so on and so forth. So this whole lecture has been about hashing, the simple uniform hashing assumption, the balls and bins model, and how these interoperate with each other to help us build some very nice data structures that are suitable for big data applications. So that's it. Thank you.